In this clip, let us look at the effect of temperature on the PV cell characteristics. There are three important parameters. One is ISC, the short circuit current, and then you have the VOC, open circuit voltage, and you have PM, the max power of the PV cell or the peak power of the PV cell. Now, how does these three important parameters vary with temperature? Let us now have a look at the data sheet and see what are the numbers and what are the values they give. Here in this data sheet, you see here there are three parameters: temperature coefficient of ISC, short circuit current, temperature coefficient of VOC, temperature coefficient of P max. These are the three parameters that we would be discussing now. See, the temperature coefficient of ISC is plus 0.045% per degree Kelvin, and the temperature coefficient of VOC is minus 0.34% per degree Kelvin, which means that as the temperature increases, VOC will decrease. Same with Pmax. This is understandable because the temperature coefficient of ISC is positive, temperature coefficient of VOC is negative. The temperature coefficient of power, which is the product of current and voltage, will also be negative, and that is given as minus 0.47% per degree Kelvin. So let us study a bit on how these temperature coefficients come about and what is their relationship with respect to temperature. With regard to ISC, we know that we have seen in an earlier clip that ISC is approximately equal to the photocurrent IP, which is the photocurrent. And the photocurrent is directly proportional to the insolation. Insolation is nothing but the power per meter square of the incident solar radiation. So if you see this from this relationship, with increase in temperature, what will happen to ISC? With increase in temperature, the photocurrent will increase. Why should the photocurrent increase? The band gap energy reduces. The band gap energy was 1.16 electron volts, and it will come down, and this will allow more valence electrons to jump into the conduction band, and therefore there are more free electrons, and as a result more photocurrent, and therefore higher value of ISC, short circuit current. So in summary, for the short circuit current ISC increases as temperature increases, and this is very small value. It is around 0.1% per degree Kelvin or per degree centigrade for silicon. With regard to the effect of temperature on VOC, the open circuit voltage, we have seen the relationship of VOC with the photocurrent, which is given like this, and we have seen this equation earlier in another video clip. So it is given as this relationship where this is NVT, N is 2 for silicon, VT is the voltage equivalent of temperature, logarithm of IP, the photocurrent, I0 is the reverse saturation current by I0. If you take I0 very small compared to the photocurrent, then we can say VOC is equal to NVT logarithm of IP by I0, the reverse saturation current. So apparently, if you look at this equation, it is not directly evident that VOC will decrease if temperature increases. However, you should note that VT is a function of temperature, that's T by 11,600. I0 is also a function of temperature. It is an exponential function of temperature. So considering I0 and VT effect together, you will see that VOC is inversely proportional to temperature. The reverse saturation current I0 is proportional to temperature to the power of m, e to the power of minus VGO. Recall VGO was the numerically voltage equivalent of the band gap energy by n VT. So you see the dependence of I0 on temperature, and substituting this and then trying to find dVOC by dt, we get dVOC by dt as VOC minus VGO plus mNVT whole over T. So you see that for a given temperature, we can calculate the rate VOC will change with temperature. Now if we take values, typical values for silicon, let us say for silicon, m is equal to 1.5, n is equal to 2, VT is equal to 0.026 millivolt, 26 volts at 300 degree Kelvin. That is, if we take temperature as 300 degree Kelvin, and you will, and VOC as 0.6 volts for a cell cut-in voltage, and you will see that if you apply all these to the above formula, you will get approximately minus 2.1 millivolt per degree Kelvin. What it means that for every cell PN junction, the variation of the open circuit voltage VOC with temperature is minus 2.1 millivolt per degree Kelvin. 1 degree centigrade rise in temperature will make VOC to fall by 2.1 millivolt. How did we get this equation? I will quickly run through the derivation. You can use the pause mode and try to study how the relationship this with the effect of temperature for VOC came about. So here I have the derivation for dVOC by dt. The derivation is simple, but I am not going to explain every step. I will just run through it. You can use a pause mode on the video clip and read it at your convenience. The reverse saturation current we saw was given by I naught is equal to k t to the power of m e to the power of minus Vg naught by nVt, where Vg naught is the numerically voltage equivalent of the band gap energy. M is 1.5 for silicon, N is 2 for silicon, and Vt is the temperature equivalent to the voltage. Now for this equation, take the logarithm and you will see that it falls into this kind of a relationship, and the logarithm of I naught is given like this. Then this equation you differentiate with respect to temperature T. So differentiating with respect to temperature, you will land up with m by T plus Vg naught by Nt Vt. So keep this equation aside. Next, come to the VOC relationship. We saw that VOC is equal to NVT logarithm of IP plus I naught by I naught, and if we take IP much greater than I naught, you will see that it is equal to NVT log of IP by I naught. And this is the relationship that falls as the next step. Now differentiate that. Differentiating this equation with respect to temperature, you get d by dt VOC by NVT, d by dt of log of IP minus d by dt of log of I naught. Now d by dt of log of I naught we have already derived here. So we can directly substitute this value here. D by dt of log of IP is 0, assuming that the variation is very negligible compared to the variation in I naught. So as you are having a numerator in the denominator, as you are having two terms, VOC dependent on temperature and VT dependent on temperature, splitting it up using the product rule, you get this relationship. And then simplifying, you will see that dVOC by dt equals VOC minus Vg naught plus mn Vt by t. And this is what I had mentioned earlier. The almost inverse proportionality of VOC with T. Now for silicon, if you substitute m is equal to 1.5, n is equal to 2, VGO is equal to 1.16 electron volts and VOC is 0.6, you will land up with dVOC by dt as this value. And for a temperature of 300 degree Kelvin, the rate at which VOC changes is minus 2.12 millivolt per degree Kelvin, which means that for every degree rise in temperature, the open circuit voltage falls by approximately 2 millivolts. Therefore, in the case of VOC, we see that VOC will decrease as temperature increases. Whereas in the case of short circuit current ISC, we saw that ISC increases as temperature increases. And in the case of power being a product of V into I, as VOC is having a negative temperature coefficient and ISC is having a positive temperature coefficient. So this is negative temperature coefficient. This is positive temperature coefficient. Power will also have a negative temperature coefficient. This would imply that PM would decrease as temperature increases. So these are the main effects that you would see on the PV cell parameters due to variation in temperature. Consider this IV characteristic of a PV cell and let us study the effect of temperature on the cell characteristic. We have this IV curve taken at standard insolation of 1 kilowatt per meter square and standard temperature of 25 degrees centigrade. Now let us say the temperature increases, and the temperature increases from 25 degrees centigrade to 40 degrees centigrade. What is the effect on the cell? Now let me make a duplicate of this curve. Let me change the color to green and superimpose the changed curve. The ISC will vary slightly and it will increase with increase in temperature. That's what we studied. And what happens to VOC? VOC would decrease with increase in temperature and it will decrease in inverse ratio. So the changed characteristic PV cell characteristic curve would look like this, the one shown in green. So as temperature increases, the characteristics shifts in this manner. Now consider the temperatures replaced with variables T1 and T2, where T2 is the lower temperature and T1 is the higher temperature. Now, what would happen and how would the curve look like if we have a third curve which is set at a temperature T3 such that T1 is greater than T2 is greater than T3. T3 is a lower temperature, much lower than T1 and T2. So we would expect the curve for the VOC to be on this side of T2, the red line. And for ISC, because the temperature is lower, we would expect it to be below the red line. So this is the curve that is expected for the IV characteristic, which is set at temperature T3. Now looking at the power curve, now this is the power curve for the T3 curve, and this is the peak power that the cell is capable of giving at temperature T3. Now at temperature T2 and T1, the corresponding power curves are like this, and then you see that the peak powers are decreasing. So as the temperature is increasing, you will see that the peak powers reduce like this. This is also corroborating what we just studied, that VOC decreases with increase in temperature, ISC, short circuit current, increases with temperature, and its product, the peak power, decreases with temperature.